I'm delighted to welcome fellows and visitors to this journal webinar. We apologize for the slight delay occasioned by a technical problem, which I hope we have overcome. We'll be discussing the paper entitled A Reevaluation of Fixed Effects Meta-Analysis by Kenneth Rice, Julian Higgins, and Thomas Lumley. The meeting welcomes an online audience. I'm glad to see all the attendees here. Please keep your microphones muted and your cameras turned off unless you're called upon to speak during the open discussion session later. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, let us know and we can edit that part out. If you experience technical problems online, use the support chat box and someone in the RSS support team will help you. We actively encourage everyone to contribute to the discussion of the papers in the Q&A session later. Comments or questions can be posted in the chat, and that's going to be more effective for us than trying to have people raise their hands because of the number of attendees and possible commenters. So, Kenneth Rice will be presenting the paper. It appeared in the Journal of the Royal Statistical Society, Series A, in 2018. And I now turn it over to Kenneth Rice for his presentation.
Thank you, David, and thank you everyone for being here today. I'm just going to share my slides. Can everyone see that?
Yes.
Great. So, as I say, thanks to everyone for being here today. Thanks also to Thomas and Julian. Julian is here today as well. Thomas can't be here for the other co-authors on this paper. There's been lots of extensions of it since 2018 that I'll talk about with some of the students who are listed there. So, very briefly, what I'm going to be talking about the next 25 minutes or so is fixed effects meta-analysis. And note the pedantic use of the plural S there. That's important. So we'll be getting into detail on that, as does the paper. And that differs from common effect or fixed effect in the singular meta-analysis, where you assume that all the effects in all the studies are all identical. We're not going to make that assumption. We're going to proceed without it. And this leads us to lots of discussion of what is it that we're estimating in a meta-analysis. And can we describe that in ways that are helpful and that our collaborators will understand, and when might particular approaches be better or worse ideas. As I mentioned in the chat already, then there's a URL there that you can get slides for this talk if you want to read ahead in advance or look at them afterwards, and there's lots of other resources on that page as well that I hope people find useful. So let's jump into it. Here's an applied analysis. And it's about pain. Is it going to hurt? Well, it's about pain. It's from a study of kidney transplants, and these people's kidneys were getting biopsied, and there's a number of them who are in a considerable degree of pain or not afterwards. 18 different studies looked at this, and each of them is a simple count. This is not the example that's in the paper, but it conveys the main things that I want to talk about. So it's a little bit different, and I hope conceptually simple for everybody. So we've got some counts, this RI column over here for the I going up from 1 up to 18 in this case, and the overall number of people who were biopsied, and RI is the number of them who were in pain. So a simple type of binomial setup if you want to think about it. There's higher and lower rates of pain observed in different studies. Some of these are bigger than others. There's one with 1,000 people and the rest of a few tens of people. And we want to get some overall idea of the rate of pain. So that's our meta-analysis. This is a real meta-analysis problem that actually came up in practice. And the sort of thing that one might meet with a collaborator is the slightly embarrassing question of how would these PI hats, those overall proportions on the previous slide, how would they be meta-analyzed? Well, the embarrassing is embarrassing because the answer depends on who you ask and exactly what way they try and answer the question. So we've got raw proportions. That's just seeing the number of total number in pain divided by the total number of biopsied. You can move things to a log scale or a logistic linear scale. You can do more esoteric things with Freeman-Tukey transformations and the square root of the arc sine transformation before you meta-analyze all these things and stick them together. and it matters, whether you turn these all back into estimates of the overall proportion, and it could be as low as around 1%, or it could be up around 10% as your estimate. There are relatively narrow confidence intervals around all these things, and we'll get into the details of exactly how they might be calculated later. But it's a mess. If we just go in and answer the question, how would these different estimates be meta-analyzed without a more detailed statement of what that might mean? So, unless you want to be stuck explaining why 1% is not the same as 10%, then let's answer a better question rather than this rather vague one at the top, which I think will probably be familiar to those who've done meta-analysis in practice. The better question then, one better question that you could ask, it's not the only one, but one better question is to ask, what is the overall rate of pain in people like those who contributed to those case studies? So those case studies, all 18 of them there, in that whole set of people, in the couple of thousand, 2,000-3,000 people overall who contributed there, or people who look like that, think about a bigger population, but the population of whom those 2,000-3,000 people are representative, then what's the overall rate of pain in people like them? And that question we can answer fairly straightforwardly, if we're clear about what it is we're after there. So that overall rate of pain, where I've just said what is overall in some detail there, leads to a very simple estimate that you add up the numbers in the RI column and you divide them by the total number of people that you've got in the studies. Absolutely straightforward thing. This is not at all rocket science here, that you're taking the total number of those in pain and dividing it by the total number in the studies. And that we'll call P hat F, our estimate of the overall proportion. F is short for fixed effects, which was the topic here. You can think about that as a weighted average of the individual PI hats, and the weighting that you need to do to connect those things is the weight that is proportional to the sample size in each of the studies. There. So, and this representation with the weighted average of the PI hats, which tells us what parameter we're getting at, the target parameter, if you like, that there's a true underlying rate of proportion in each of those studies. If you could sample enough people from the populations from which they're sampled, there would be some overall rate of pain, call that PI, and a weighted average of those with weights proportional to the number sampled from each of those subpopulations, if you like, gives us an overall parameter, PF. And that's a particular average of the study-specific PIs. That's the thing that we're estimating when we do this, or that's the approach that we put forward in the paper. Here, a slight detail that's really not important for things today. I'm just conditioning on NIs, on knowing the NIs, and doing everything conditional on them. In the paper, we use a parameter E to I to much the same effect. So there's a slight difference there, but it's not going to affect things that we'll talk about today. Why call it fixed effects in the plural, that pedantic bit? Because there are k fixed unknown rates in each of the 18 populations that we have sampled some people from. And so that's why it's fixed effects, plural. Our meta-analysis estimates an average of them, and that's not the same thing as saying they're all identical. That would be common effect or fixed effect in the singular meta-analysis, where you're assuming they're all identical, which is obviously not plausible in very many situations at all, but we're not making that assumption here. They're all different, and we're just estimating an average of them. Through this PF hat, this simple add up all the R's and divide by all the N's, we learn about populations of the studies that we've got, and that's something that we get more into in the paper in a bit more detail, but it's also not new. Larry Hedges has been publishing on that for some time. Citations are in the paper there, but learning about the learning conditional on the people that you happen to be observing is an idea that's been around for a while, and we try and formalize it and clarify it a bit in the paper there. We think it's a good default, as I'll be talking more about, but it's certainly not the only thing you can do, and it's not perfect either. In particular, a point that people often make is we're not generalizing or predicting the next study that comes along. We're only talking about the sorts of people that we happen to have observed, and that is some sort of limitation. You can do a lot with it, but it's not answering every possible question. But it is answering one question, and why this overall average. Well, this is an idea that we'll come back to, but yeah, what would you estimate if you could pull the data? Typically in meta-analysis, then we can't pull the data. in this we can, because it's just some ones and zeros in particular counts, and you could put them all together. And if you did, and you probably could put it somewhere in table 1 of the analysis of such a study, or such an analysis, that you would say what the overall rate was. We have a few thousand people, and about 1% of them had pain after their biopsies. And so that's a question that you can answer by pooling the data together. But more generally, to think about which meta-analysis we're going to do, I think it's a good question to ask, what would you estimate if you could pool the data? And in situations where you can't pool this data, it's still a relevant question. It still helps us formulate which type of meta-analysis we're going to do. Okay, some details here that I won't get into today, but yeah, for this meta-analysis of proportions, then it turns out you can get exact frequentist inference, the exact meaning the same type of exact as Fisher's exact test, or exact confidence intervals for binomial proportions, say. And it does use the same machinery as exact confidence intervals, Klopper-Pearson or Laker intervals for binomial proportions. You can just use that, plugging in the overall number of people in pain and the overall number of people in the study, and there you are. There's your confidence interval, and end of story for getting the frequentist inference out. So that's very simple. There's no continuity corrections needed. We don't need to go adding a half to small cells. We can cope with zeros. We don't need to tell people what an arc sine transformation is or its square root. Any of that silliness, frankly. So it's very straightforward. It can be slightly conservative, but you can estimate how much. Yeah, not a problem. Anyway, inference is available, and we can get confidence intervals and p-values and things out without too much difficulty. But that's fine for learning about the overall rate, the overall effect more generally. But what about heterogeneity? If I report that point estimate, that's 0.043%, and there's a confidence interval for it, then yeah, we'd fall into the floor of averages, as this cartoon shows, that you can drown in a river of average depth 3 feet, because it might not be 3 feet deep all the way across. It might have a deeper point here, and you could get very wet indeed there. That's not to say that average depth of 3 feet, that's not useless information. It still tells you that, for example, if you want to get across this river, then a pair of wellies isn't going to be enough. And you know, that's useful information, but it's not the whole story. And similarly over here, then there's our meta-analysis and putting it all together. Then we get an overall estimate, which tells us about the rate of pain in all the people in the studies that I just talked about. It's still meaningful, and as just mentioned, we can get valid inference on it, but heterogeneity is still important. The fact that yeah, it looks like the rates are higher in some studies, lower in some other ones, is useful information that you probably want to say something about, and that's fine. It doesn't mean that the in overall fixed effects meta-analysis on the PF thing is meaningless. It just means that there's other questions you could answer, which again is an idea that most people are comfortable with, but maybe not everyone. Okay, so how might we address that? And this is from some of the subsequent work. Then if you want to summarize that spread, then obviously there are common tools in the meta-analysis literature. One thing's about Cochrane's Q for measuring heterogeneity in a way. Also I-squared, which I have to mention because Julian's here, and that's yeah, hugely popular as well. Here's a slightly different way of doing it. And all we're doing is taking a weighted variance. We met weighted averages before, but weighted variances exist as well. This is a weighted variance of just the PIs, the study-specific true rates of pain, and how they differ from the overall weighted average PF that we've met before. Square those and add them up, weighted by some weights that are proportional to sample size, and that's a measure of variance. It's a weighted variance. So that's a weighted variance of the PIs. It turns out it's also the excess variance that you get in the estimate compared to what you'd have under homogeneity if all the PIs were equal to PF, which is also a different and slightly more abstract way of thinking about heterogeneity. But importantly, it's measured on the proportion scale. And if you use a very simple plug-in estimate, then you get an estimate of about 0.06 in this case, 6 percentage points. And so in the text here in italics at the bottom, we'd estimate that sampling pairs of individuals from the overall population that I've talked about already, we'd expect their study-specific rates to differ by about 6 percentage points. So take people from different studies, and how much might their study-specific rates of pain differ? Well, by quite a bit. And that's another way of saying that, sure, there are going to be some groups of people or some people in some study populations who have higher rates and some who have lower rates. And this 0.4 is what you get, 0.04 is what you get overall. It's the average, but there are some higher and some lower. And by expecting them to differ by about that much, depending on which study you're looking at, wouldn't be unreasonable. It also doesn't say they're all that far apart, or that people met standard deviations before and compared them to overall estimates. So that's what we're doing here. And yeah, it's measured on the proportion scale. It's measured on the same scale as the original estimates. And therefore you can interpret it and say whether or not it looks big or small compared to that overall average. And we'll come back to that idea soon. So moving on. So I've talked about proportions and their meta-analysis, but as in the original paper, which I'm assuming people have had a chance to look at, then that paper was about regression estimates. So let's look at analysis with some regression estimates instead. This is a very classic meta-analysis setup. We've got a whole bunch of beta hats from, in this case, 6 different studies. We know their standard errors essentially, and we're going to put them together. In this case, this is the one from the paper. Then all these beta hats are measuring the difference in blood pressure per copy of a particular genetic variant that you may or may not have 0, 1, or 2 copies of. And these are all from linear regression, very straightforward regression, regress your blood pressure on this genetic variant thing, and report the slope from that linear regression with its confidence interval, and that's what we're doing in 6 studies. Because these are all 6 large studies, it means that approximate normality is not our biggest problem here, and the central limit theorem tells that they're all estimating some true underlying slope or trend, if you like, in each of those study populations, given by the names there, and we know their standard errors. We'll call them sigma I. With negligible error, we can relax that assumption, but it's convenient to keep it for now. So the big question there: what would you do what would you estimate if you could pool the data? And if I gave you this sort of study, there's the 0, 1, 2 thing, the genetic number of copies of a genetic variant that you have. There's your blood pressure for a whole bunch of people in, well, just 3 studies here for simplicity. That there's a little bit of a trend in each of the 3 studies. There's also some potential confounding going on here, that the variant is rare in the red people and common in the blue people. So you don't want to do an unadjusted analysis. But what I think most people would do, and what I'd encourage them to do, at least as a default sort of analysis, would be to regress outcome Y, blood pressure on number of copies of the variant allele X, and adjust for study. So adjust for factor of study. And kind of stratifying the analysis that way. And if you do that, instead of getting the color-specific linear regression lines that are fitted, the dashed lines that are fitted there, you get the slope of the purple line in the middle. The slope is the important thing, the fitted slope from that linear regression that adjusts for study. And that's would be a reasonable summary of the trend overall in the pooled analysis, where you're taking into account the fact that it was pooled and the data came from 3 different studies there. So if you could pool the data, then that's what we produce. And that's essentially what we get from a fixed effects plural meta-analysis. Our estimate is a weighted average, precision weighted average of the individual slopes. So the slope of the red line, the green line, the blue line on the previous slide, and you weight them according to a couple of things. One is how many people are in each of the different studies, and then how noisy is the data in each of the studies. Formally, that's Fisher's information about the beta I in each of the study populations, and you combine them there. But that's the standard error, 1 over the standard error squared. They're providing the weights. And what that's telling us about, well, is a weighted version of the underlying slopes in populations 1, 2, 3 up to K. So it's a weighted average again, very much as we saw the same for the proportion stuff earlier on. And it's just a weighted average with weights that you assume with negligible error. And so it's just a weighted average of normal things. And that's very straightforward to work with algebraically. Then we can get exact confidence intervals for what we call this thing beta F as the parameter there. And that's, I say it's easy to get inference on that. It gives you the same point estimate and the same confidence interval as fixed effect in the singular meta-analysis, but the interpretation is different. We're just looking at an overall estimate. What's going on in each of the populations, in each of the K populations might be different, but we're looking at an overall average, as I hope this expresses. Under homogeneity, if the beta i's are all exactly the same, it turns out you're estimating exactly the same parameter as pooled study-adjusted analysis with no efficiency loss. That's a nice result due to Daniel Lin and one of his students, that you're not losing any efficiency by doing meta-analysis instead of pooling all the data and doing that adjusted analysis that I mentioned. Under heterogeneity, it's a little bit more complicated, but you're estimating the same as a pooled study-adjusted analysis that weights in the ways that I've described here. And still useful, and any efficiency loss compared to being able to pool the data and doing it that way is minimal. So in the 2018 paper, we argue that the same default is an overall summary of what happens in people who look like those in the case studies that we've got. To put that into practice, there's the forest plot we saw already. There's the overall estimate of beta f, and there is its point estimate confidence interval. You could report it saying that combining the 6 populations, and maybe talk about the weighting, then on average each extra A allele is associated with a 0.45 millimeters of mercury, lower blood pressure, and there's the confidence interval for it. So the average there is across the combining of the 6 populations. So we're reasonably clear there, I think, that we are combining them and just estimating an average effect overall. In this example, then the focus is from a GWAS analysis, and there we're really just looking for signals and not too fussed about how big they are. I recognize that's not everyone's modus operandi, but there the focus is on the strong null that all BIs are equal to 0. Is there anything going on in any of those studies? If so, that's interesting, and we can learn some new biology from it. And you can get that from a test of whether that overall parameter, beta f, is equal to 0 by testing in the usual wall test sort of way. Heterogeneity is still worth addressing. You could still ask how much the effects differ. These are different studies in different places, in different sorts of people, in older and younger people, in well, more and less American situations. Some are in Europe, some are in Iceland, and some are in the States. And are there patterns for study, which I'll briefly address here. For the heterogeneity, well, a little bit more time on it because it's not in the original paper, but sure, there's a measure of overall variance, the weighted variance of the beta i's around the fixed effect average beta f. And that's a weighted variance just like the one we talked before about with the proportions. Call it zeta squared because we're running out of names, things to call things. And sure, you can do a plug-in estimate for it, and that's really just a rescaled version of Cochrane's Q. So this thing connects to standard tests in a straightforward way. It turns out it's much stabler, and we wrote a paper on this, than similar measures of spread that you get from things like Dersimonian-Laird or Remmel estimates of tau haps squared in a random effects analysis. There's a variance in there, or a standard deviation in there. This one concentrates on the studies where you have more information, and that makes it stabler. So that's a good thing. And in our blood pressure GWAS, then remember we had the point estimate down here of about 4 or 5, and zeta is about 0.2 millimeters of mercury. So the spread around there is somewhat noticeable. And does that matter? Well, for the testing purposes, I say just looking for any signal in any of these studies, then probably no, it doesn't. If you were building it into some form of prediction about who's going to be getting antihypertensive medications, then maybe it would. Notice that the scale is important there. If I showed you the same data, but it was over here, just shifted, everything else kept the same, then yeah, zeta 0.2 probably wouldn't worry you too much because it's very small compared to the overall effect and the effect in any of the studies. Here, that's in the original data, then that's not the case. So being able to talk about spread on the same scale as point estimates is, I think, important, and it's not something that we get from Cochrane's Q. We don't get it from I squared, and it's the combination of those two. And if we're going to combine them, let's put them on the same scale. The point estimate and the measure of spread, I think, is a very useful thing to be able to do. Just briefly, then, what else can be done about heterogeneity? Well, weighted averages crop up in basically everything in the paper, and they could be more or less complicated ones. You can get weighted averages of the effect size and how they differ from the overall beta f, and that gives you meta-regression. It turns out this is fixed effects, plural, meta-regression, where we're just viewing the slope that we get out, this is a linear regression essentially of the beta i's on their study-specific x's, whatever that study-specific covariate is, and we get a trend out of that saying that the beta i's are bigger or smaller in studies with higher or lower values of x. We can build that into tests and look at deviations from homogeneity in the same sort of way that we're doing Cochrane's Q and there. Neatly, I think there are decompositions of overall measures of signal to noise. If you take the Z statistics squared, so beta hat divided by the standard error squared in each of the studies, and then up, it turns out that's the same thing as the signal to noise squared in our fixed effects meta-analysis for the overall estimate plus Cochrane's Q. You can also think about breaking down Q into, well, an overall test of this overall slope thing plus what's left over in the noise there. And you could continue that to many different levels of decomposition. If you like, it's the same mathematics as analysis of variance, actually slightly cleaner there because we're assuming that we know the standard errors in each of the studies. So just to illustrate that, and this is from the paper, then sure, here's our meta-regression. There are the 6 different studies. That's the overall estimate. I plotted it at the average age, and the straight line there is the trend, which says yes, indicates in this data that there seems to be a trend that the genetic effect of the variant on blood pressure seems to be higher in studies with higher average ages. So there's some language to report that, averaging over all studies. We estimate that the genetic effect on blood pressure is higher by 0.02 or so millimeters of mercury per copy of the allele per 1 year difference in average age. So some language to describe what you're getting there. It's all measured in units that people can hopefully interpret and make some sense of connected to the science that they're doing. Then last couple of things. Why not use random effects meta-analysis? We talk about this a little in the paper, and it comes up a lot in discussions of it. I've talked about the fixed effects analysis here in the middle most of all, where there are a whole bunch of effect sizes and you want some, and we're going to estimate some average of them. That's compared to the common effect situation where you assume that they're all absolutely equal, which is not plausible for the genetic effects. It's not plausible for the pain analyses, that we do different studies in different people and should expect different things to be going on. But the alternative that is pushed in a lot of places is the random effect, that assume all these beta i's are coming from some distribution with a mean and a variance, and work from there and get an estimate of the overall mean and the overall variance or standard deviation, the tau thing that we've mentioned a little bit before. Difficulties there. Unlike random effects models, the beta are typically not random sampled. People who are doing the later studies in a meta-analysis should have looked back at the earlier studies and tailored their design to take that into account. If you're trying out some new treatment, then it's probably going to happen that you're going to try it in people in whom you think it works better. So looking back at the data, then you'd have some idea about that, and that's violating typical random sampling assumptions that are going on here. If you want to do predictions, then sure, there's not very many better options are available, a few, but there's a little literature on that. The other thing that people appeal to there is an appeal to exchangeability, which motivates fitting a model like this. So doing the calculations that involve fitting the random effects model, sure, but it doesn't actually motivate estimating the mean of that random effects distribution nu, as it's written there. It just says that in a Bayesian sense, then, hey, your prior has to look a bit like this, or has to look exactly like this, but that doesn't mean that we've got to estimate the mu mean of the distribution there. A really weak argument that I see a lot is because it gives wider intervals. Another way of saying that there will be less, and it sounds like, oh, we're being conservative and trying not to do too much harm there, which is, you know, an honorable goal. But if I said this, because it chucks away data, you'd be less keen on this statement, but it's the same thing. So I think we should try and be efficient, do efficient analysis where we can, and just appealing to slightly wider intervals in most cases is not very compelling. Quote from the Cochrane handbook there, which I think is good on this part, that the random effects model does not take account of the heterogeneity in the sense that it's no longer an issue. We still need to think about heterogeneity and argue that we're doing that with the zeta and delta that I showed you earlier about the difference in effect sizes across the studies that you've got. Okay, lots of stuff that it's not time to talk to today. There's been lots of work since the 2018 paper, Bayesian stuff and relaxing the important assumption. I know people are keen on that. So David's done some stuff on that, but I published a paper with one of my students too that relaxed that assumption, and it turns out not to matter too much. And we can say when, and it matters more when it doesn't. 2x2 tables are interesting, challenging, but we can pretty much fix that. And there's some work in progress there for new things that are coming at you soon. So in summary, fixed effects in the plural methods have simple and useful interpretations, argued, even under heterogeneity. You can say what they're estimating. It may not be the whole story. It may not be the only useful thing you can do with the data, but it is something, and we can report it. And often it's very useful. If you want to do something else instead, then think about what would you do if you could combine the data. I think that's a good way to answer that question. And yeah, specify what question you do want to answer. I think it's reasonable to make people say that when they specify why they're doing fixed effects or random effects or whatever it is that they choose to. And if you want to do something more esoteric and unusual, then that could be fine in different circumstances, but say why. So that's the overall message. Many thanks to everyone who's contributed here, Thomas and Julian, of course, the co-authors on the original paper, and the students I mentioned earlier who helped with all the later stuff. The RSSA reviewers, and thank you for your contributions back in the day, and to all discussants today, and particularly to Peter and David for setting everything up. And thank you for attending. There's that URL again, but I will stop there and and see what other people have got to say. Thank you. David, you're muted.
Thank you. The technology wins again. I have unmuted myself, and so thank you very much, Ken. I think from your presentation, we have lots of food for thought and interesting ideas to work on, and we do have a planned discussant, Peter Diggle, and I would hope we can hear from him now.
Okay, thank you, David. How's my volume?
Your volume is fine, Peter.
Okay, great. I'm going to share my screen, if I may. And I now need to find a slide, which I was expecting. That's the wrong slide. Well, it's a slide. Let me find the slide plural. Forgive me, they were there not long ago. Okay, there's a lot to like, certainly to be liked by me, about the paper and the talk. And in particular, what I really like is the way Ken's gone into the idea that when you're doing any kind of meta-analysis, and let's start with the fixed effects meta-analysis, you need to be very clear what your inferential target is. And simply saying, I want to estimate the average isn't enough. And I think there are other areas of statistics where, again, a simplistic view that you're trying to estimate the average can lead you to estimate completely the wrong thing. Now, when you actually choose a method for analyzing data, be it in a meta-analysis context or elsewhere, two questions you have to ask yourself is my method of analysis valid? And what I mean by that is, at least to a reasonable approximation, any probability statements you make about your inference are correct. And the other question is my method of analysis efficient? And I do have this rather general feeling that there's always a balance between efficiency and robustness, in that you can buy efficiency by making additional assumptions. And you can do that in various ways for various statistical methods in various contexts. And the simplest example of that, I think, although it may be that one of Ken's slides says you can have your cake and eat it in this sense, is that if you do a fixed effects meta-analysis, you're basically looking at a bunch of averages. Those are the extant data points. And underneath those are some individual data points which you can't see. And what I think you do as a sort of default option expressed in terms of a parametric model is you assume that the sample means are normally distributed with variances which are inversely proportional to the number of observations that led to each of the averages. And the additional assumptions that I kind of think must give you some extra efficiency if they're true and you exploit them, are that the variance may be common to all the underlying individual observations, and the mean may be common to all the individual studies. That's perhaps not to say that I think one of Ken's results suggests that actually you can get away with not assuming the mu i's are equal, but still getting full efficiency, which is rather nice. But to contrast that with random effects meta-analysis, I think what most people mean by that is something like the following on this slide. Again, your extant information is a set of sample means, and now your latent information is not only the individual observations, but also some things which we call random effects. And I think the standard assumptions that people make is that those random effects are exchangeable with a variance tau squared, say, and that conditional on those random effects, the mean in the ith study is the overall mean plus that study-specific random effect. And the first thing that that does, I believe, is it means that your estimate of mu would not necessarily be the same as in a fixed effects meta-analysis, because the relative weighting that you would give to the different studies will not just depend on the NI, it will also depend on the ratio between tau squared and sigma squared. Now, trying to get my head around how one might approach a meta-analysis in a slightly wider framework, I guess I tried to distill it down to this equation here, because you've got some y's, which are measurements, and you've got some u's, which are latent random variables, if you're prepared to admit that a random effects and meta-analysis might be useful, which I think I am. And you can always factorize that as y conditional on u times u. Now, you've now got at least 3 questions rather than just 2. One of them is the same as before, which is you need to be very clear what your inferential target is. The second one is, and again, Ken talked about this in his talk, where does the heterogeneity come from? But the third, which I don't believe he discussed, is in the context that you're dealing with, is it reasonable to assume the UI are exchangeable? And to show why that might matter, I'm going to make what some people may regard initially as a tenuous analogy by considering a geospatial problem in which there's some phenomenon which occurs in this square region, and what you want to do is estimate the area-wide average value of this phenomenon. So if you like, the integral of that surface over the complete area. And a simple way to do that would be to take some measurements at sample locations within that area and to take the average observed value. And provided you obey some basic rules about where you put your measurement locations, of which the most obvious is choose them at random, then you can validly estimate the mean as 41.3 and attach to it an uncertainty of plus or minus 8.6. Now, in contrast, if you want to make a predictive inference and you're prepared to actually posit a model, stochastic model for the spatial variation in that underlying colored surface, which you never see in practice, then under assumptions that the data and the underlying surface here undeniably satisfy, because this is actually a synthetic example where I know what the truth is, then your predictive inference would give you almost identical point estimate or predictand, but the standard error is deflated by a factor of about 5 or 6. And that's not atypical of results that we found when we're dealing with combining what are disease prevalence surveys in studies of disease prevalence in low and middle income settings, where the data are often sparse, and we really need to, well, we believe we really need to add some modeling assumptions to extract from those data the best possible answer to the question that public health people need to know, which is how does the prevalence of disease vary over the whole area, which in real examples would be a country which is subject to a particular disease that needs treating. Now, you might think that's tenuous, but just to close my contribution, the point of this example is that data at one location are informative of prevalence at neighboring locations. And there may be an analogy, I think, in Ken's analysis where he looked at results as a function of age, where if the response to age can't adequately be described by something simple like a linear function, could it actually be modeled as essentially a random effect, with studies from patients close in age being more similar than studies from patients far apart in age? Just a suggestion. Okay, so I want to finish my little contribution by going perhaps beyond what people would think of as meta-analysis. I mean, it seems to me that meta-analysis is everywhere, because we really often we should want to combine information from multiple studies, and we might want to do that in ways where the individual studies are perhaps rather more loosely related to each other than in the textbook examples and in Ken's very nice exposition. So it may be that the term data synthesis would cover what I'm trying to get at in this diagram. And really, this diagram has its origins in the work of a collaborative group set up by the Royal Statistical Society jointly with the Turing Institute during the recent COVID pandemic, in which a group of statisticians were funded to meet weekly and work with the national public health agencies to identify research questions that needed some non-routine statistical thinking to provide useful, quick answers to policy relevant questions. And so the context of this diagram was that the target for prediction here, would be what is the prevalence of COVID in the country at any one time? And there are many different studies that could be, and in many cases were being done during the COVID pandemic, which gave different answers. And those studies might not have had any similarities in terms of the detailed design. We could have had a case control study, a cohort study, a randomized trial, but we were able to believe that there was a common element T, which is the true prevalence of disease, which is the thing we're trying to get at. And the collaborative group that I mentioned had a lot of people in it, and most of them got their names on the paper that describes this under the name of interoperability of statistical models. And the idea here is that you can spend quite a lot of effort making sure you really do get a good analysis of the case control data, ditto the cohort data, ditto the RCT data, but then, and only then, do you fuse or synthesize those three models into saying, how does that common underlying element T affect each of those separate designs? And then you give your sort of final inference. Okay, that's all I have to present, but I do think it's a lovely paper and a lovely talk, because it does actually make the message very clearly that it's easy to criticize a simple method because you think it's making strong assumptions. And in fact, often it's not making such strong assumptions. It's making rather weak assumptions. I think it's probably the case that in general, when you make weaker assumptions, you buy robustness and lose efficiency. But it may well be that in the definition of meta-analysis that Ken's adopted in his paper, which I believe is the standard one, that there is a little bit there of having one's cake and eat it. So thank you very much, Ken, for that really nice exposition.
Thanks, Peter.
Thank you, thank you, Peter, for an interesting and stimulating discussion, which moves us in another useful direction. I hope we can now hear from some comments from among the attendees. I think I'm going to have help from from Anna Varela of RSS in identifying people who've put comments into the chat so that they can be called on. Well, okay.
We don't have any comments as of now. Oh, we've got someone. Would you like me to read it out, or David, would you like to read it?
Let's see, can I? Well, it's a couple, 3 paragraphs, which I suppose I can read just to get it into the record, and then maybe the person who contributed it, although it says the message has been deleted. Sometimes there's also a question about what data you will end up identifying. For example, if all studies are the same dose, same drug, and reflect a sensible target population that I would use for prediction when treating a patient. I think in many Cochrane reviews right now, random effects model and fixed effects model are both presented. I'm not sure that the commenter is referring to fixed effects plural there, but anyway, I believe many would see it as a form of sensitivity analysis without knowing that the inferential target changes. In relation to this question, how would one write in a statistical analysis plan on what should guide our decision for the chosen model? We are often limited by the data we have available, e.g. limited trials for a given treatment. What would we do? So we have that, and with having read all of that, perhaps the best strategy now is to let Ken comment if he wishes.
Sure, I can take a stab at that. Particularly for the statistical analysis plan, I mean, I do sympathise in running such plans myself. For the chosen model, I think the answer there is, yeah, which population do you want to know about? And in that particular clinical trial setting, then I think that, yeah, the most relevant one, at least by default, is putting all the people together and adjusting the study, as I mentioned. So there I would primarily, if it was me writing the analysis plan, I'd put forward the fixed effects plural meta-analysis as the primary thing. Just to get reviewers off one's back, then I think it's unavoidable in practice to have to do the random effects, as you mentioned, as a sensitivity analysis, and that's fine. But we do talk about the setting of clinical trials in the study analysis, and kind of related to the genetics example. That's a situation where I think a focus on testing is somewhat legitimate. It's not the only thing you could do, and estimates are useful as well, but I'm making a compelling case that there is some effect in a good direction, one hopes, and that it's beyond chance. It seems like a good way to go, and you've probably got, not absolutely always, but you've probably got the best chance of getting that from the fixed effects meta-analysis and the wall test that I talked about. So that's probably where I'd focus in the statistical analysis plan on that, and including the other things, the sensitivity analyses, I think would be fine too.
Okay, I should remind the attendees that if they'd like to contribute to the discussion, other than putting messages in the chat, they may raise their hand, and Anna will spot them and let us call on them. I don't think I gave Ken an opportunity to respond if he wants to Peter's comments, and so I didn't want to short circuit that. If you
Sure,
wish.
Maybe I can do that now. First of all, thank you, Peter. That was I enjoyed your discussion there. With the efficiency bit, then the main result there is under homogeneity. If the effects are all the same, then yeah, this is a nice result where you don't lose any efficiency by doing a meta-analysis over pooling the individual data. There's some discussion in that paper by Daniel Ling and Zheng, I think it is, that outside of that situation, then you don't lose much efficiency. You could also argue that there's no particular alternative to what you do there. So is it really an efficiency loss? But there's not a lot there. That's also backed up by some much older work from Mantel-Heinzel estimates of 2x2 tables, where there was lots of theory proved years and years ago that, again, under homogeneity, then that's an efficient way to go in a particular sense. And if you step outside of homogeneity a bit, then you don't lose any important efficiency loss. You really have to contrive to make it a big problem there.
Okay.
Then,
go ahead.
Yeah, I see Nick Longford's asking a question, but
right, we have a comment from Nicholas Longford, which says, the average of the treatment effects over the populations represented by the studies.
I think there's more to come in that comment.
Yeah, I'm sorry, I pressed the carriage return by mistake, but I can sort of follow up on this. So my concern is that some populations are studied just far too much more than others. And therefore your statement that we want to know what is the average of the populations that are represented by the studies, well, in that regard, some studies are more important than others. Studies that draw from some sort of standard population, the population that is used in several of the studies, well, surely they should be less important. By the same token, I think that some studies are more relevant because, for instance, their quality is higher. But sort of if we don't want to go into that, some studies are more important because they are more recent.
Sure. Yeah, sure. And all of those things one can take account of with different weightings. The fixed effects weighting, which does include precision that you mentioned. I think paying more attention to studies where things are better measured happens reasonably automatically there. If one wants to go outside that, then sure, go ahead and do that. Come up with some weights that reflect a population overall in the analysis that you care about. Say what they are and why you're using them, and that's fine. There's no problem with that. I think it's fairly challenging to do that in practice. In many situations, you need to have a good justification for doing that. It sounds like in your example you do, and no problem with using that. But as a default, then with the fixed effects approach that I mentioned has a lot going for it.
Seems to regard that in the framework of sensitivity analysis and do the kinds of reweighting that Nicholas is referring to and see how much difference it makes. Earlier, Ken, in the discussion, you tossed in the term representative and the possibility that the studies you have in hand are somehow representative of a larger population. Representative is a very slippery term sometimes, and back many years ago, I think William Kruskal and Frederick Mosteller wrote a series of papers that appeared in the International Statistical Review about uses of representative in various literatures, including the statistical literature, and came up, I think, with 8 or 10 distinct definitions that people seem to have in mind in the statistical literature, one of which sadly was The Emperor's New Clothes, illustrated. Each was illustrated by a cartoon. So I like to be careful about that term. But the studies you have in hand are the ones you have in hand because of the ones you found, and not necessarily because they're the result of any process that would produce representation. That may or may not be an issue. And if we want to borrow from survey sampling, we could conceivably regard each study as a stratum. And along the lines that Nicholas was mentioning, I think weight by using weights that are appropriate for the particular strata to combine the whole. And that's a different weighting from the sample sizes you used, but another principled choice, it seems to me. Again, those are weights that are in some sense known. It looks like you're about to comment on that, so why don't I
well, I was
pause and
going
let
to say
you.
Well, for the connection to survey sampling, then Thomas, long as he's not here today, would be the person to comment on that with more authority than me. But I mean, Thomas is an author on the paper, and we do think a lot about the weights and things that come out of survey work and how they connect to what we discuss in the paper. Representative, I agree, it's a slippery term. I see the differences there. I guess the closest thing I was thinking of is that there's a Fisher line somewhere, and I think it's an experiments where every random sample is representative of some population. And you have to say what it is, and that's important that you do so. And if it's a completely kooky, unusual population that you wouldn't be interested practically, then that's important information to know. But the data is representative of it. And thinking in those terms, I think, helps unpick some of the difficulties that you mentioned. Peter's got another comment there.
Shall I read it, I think, or well, that's probably the most efficient way. It says a tangible example of NL's point would be a set of prevalence surveys from subpopulations of different sizes, where the natural predictive target is population weighted prevalence. And that's what he's summarizing more coherently the point that I was trying to make in connection with surveying. So that's very useful to have.
I would, if you have a different population or a population to which you know the connection between the studies that you've got and that population, then sure, weighting in that way to make it representative seems totally sensible.
Yeah,
it's different to what we propose, but it's answering a different question, and that's fine.
In a different, more technical direction, before we finish, I would like to toss in a caution about Cochrane's Q and I squared. The problem that people are usually not aware enough of is that the null distribution that is the basis for the customary test for homogeneity based on Cochrane's Q is not the correct null distribution. and that undermines those tests and takes I squared down along with it. So that's a non-trivial issue, and it seems not to be well appreciated in the literature. So
yeah, I thought you'd mentioned that, and yeah, see the bit where it's cited in the slides. So yeah.
So it's and overall, I think there's a problem that I see as a reviewer of many investigators who think meta-analysis can be done almost at the opposite pole from the points you've been making about needing to be clear, and as well as Peter did, about the target and the target population. They think it's a matter of putting the data in the computer and turning a crank.
Sure.
And it almost never turns out well. But I think we've pretty much used the allotted time, and so I thank everyone for their contributions, and make the closing announcement that full details of all upcoming journal webinars are available on the RSS website and announced in members' newsletters and on the RSS LinkedIn page. And if someone attending would like to receive an invitation to future journal webinars, you can send email to journal@rss.org.uk, and they'll be glad to add you to their mailing list. So I would like to thank everyone who joined us today, especially Ken for, again, a stimulating presentation, and Peter for his stimulating comments. And I think at this point we can close the session. Thank you, everyone, again.
Thanks, everyone. Bye.
Thanks very much, Ken.